I'll start the recording. So just to say, I'm going through the MPI code here, just as a warm up. We really ought to use non-blocking here, but I just use send receive. So we send up and receive down, send down and receive up. So basically, I send my extreme boundary, which is nloc, which is my top one, and I receive that into my halo, and then I receive into the other halo, the down one. Then the nmove local is exactly the same. The update road is the same routine, but I have to globally sum it. So nmove local is now I have to globally reduce and I copy back. So it looks suspiciously the same. Although if I look at traffic_lib.c, which contains the update road. Now this update road is exactly the same routine as we have in the serial code. It's just that when we call it, we pass n as n local. But if you look at this, it's not immediate. I mean, this maybe a bit bigger. Not immediately obvious, but this does the logic. If we have a look, yeah. So basically, we loop over the road. If the old road is full, okay, then if the next one is full, I don't move, so the new road is full. Else, if the next road is empty, I become empty. Else, if now if the old road is empty, if the downstream one is full, I become full. Else, I become empty, and the number of moves is counted here. I don't count in both branches because that would double count. A move is either a car leaving or a car entering the cell, but not both. So that's basically it, and I could run it, but it's not particularly interesting. But the important one, so that's the MPI version. But let's look at the OpenMP version. And the important point about the OpenMP version is that the code here is all very similar, but you declare the array to be the global size. So OpenMP is dynamic. You declare big shared arrays, and at runtime, you say, I want lots of threads to work on those shared arrays. And by default, arrays are shared. That's why I have to, you have to do special stuff to make data private in OpenMP. So in MP, everything is private. There's no shared data. Any data you allocate, well, we'll see, there are new routines that allow you to have shared data, but by default, there's no shared data. In OpenMP, everything is shared by default, and you have to make things private. So these arrays are, in my terminology, on the global whiteboard, and the threads are all sitting there waiting to work on them. And so actually the code looks almost the same. I have a little routine to say how many threads I'm running on. I can initialize. So this runs in, so if you don't see OpenMP directives, the code runs in serial. So I just did initialization in serial, okay? But this looks exactly the same, except I've done two things. The update road will be parallelized, and I've parallelized the copy back. Okay, I could choose not to parallelize the copy back, in which case, if something isn't parallel, it runs on the master thread, which is thread 0. But this runs in parallel. This is saying launch a bunch of threads as an OpenMP parallel loop, and the end cell, old road, and new road are shared. And the I is a private variable, but that's done automatically. I don't have to parallelize this loop, but the performance suffers if I don't. But the interesting one is in traffic lib. Remember, in the MPI code, the difference was that we had to manually call an MPI or reduce to update the number of moves. How do we do that in OpenMP? Well, all I do is #pragma_omp parallel for shared, and the magic is reduction n. So this is all OpenMP parallelizes this loop, splits that up between different threads, all by magic. But I have to say that the n move it needs to be reduced across threads. So that's the kind of magic there. And if I make, there was a bug in my make file, but if I make this, okay, I can run on the export OMP num threads equals 1 / traffic. So it ran it. It's very quick. surprisingly quick. Have I got a different size of road? No. Okay. That's because, okay, it's because I compiled the previous version. I compiled with GCC without any optimization. That's why this is going a lot faster. Okay, that's just the make files. But if I now, so that ran at 500 megacops in 0.36 seconds. Let's run it again. It runs at twice as quick, almost. It's amazing. Let's I'm on the login node. I shouldn't really be doing this, but. And it runs, so it's not perfect, but for 4 lines of code, a couple of parallel directives, I'm now going 4 or 5 times faster on 8 threads, which isn't bad, and it gets exactly the same answer, I believe. The other interesting thing is, if I time it, you'll see that I get a real time, a user time, and a system time. And you'll see here that the user time is bigger than the real time. How can I use more CPU? Well, that's because I was using multiple threads. So this is about 8 times bigger than that because I ran on 8 threads. So that's how you can tell. This process used more CPU time than it did real time. How can a process use more CPU time than it did real time? Because it had multiple threads which were running in parallel. So that's just to kind of give you, so hopefully you've got now a view of the parallelization strategies. MPI, we manually split the road up into small sections, manually send and receive at the boundaries, manually accumulate and update it. In OpenMP, we just declare the global arrays like the serial code, but loop by loop we can say, please do this loop in parallel. There are 2 computationally intensive loops here. One is the update road and the other is the copy back step. You might not think the copy back step is very important, but on 8 threads it ran at 2000 megacops. If I just delete the copy back, let's just do the copy back in serial. So that will now go in serial. Let's run it. It's now no faster than the serial code. So that is the problem with OpenMP, that although the model allows you to pick loop by loop whether you parallelize them or not, if it's some loops, you need to actually parallelize all the loops really. So all I've done there is I've done the calculation in parallel, but the copy back in serial, and I've completely messed up my parallelism. It goes no faster than the serial code. So you might think a copy back isn't very expensive, but for a whole bunch of reasons it is here. So anyway, so Giovia said a comment. Practically, it's much more autonomous then. Yes, OpenMP is magic, but it can do it because it relies on there being a shared memory. MPI cannot do this because it cannot access the memory on another node. That's not possible. You have to manually send and receive messages. OpenMP is kind of magic. Yes, it's very. You have compiler directives. It just does it magically, but you go beyond a single node. You could not run on more than 128 CPU cores. So ARCHER2 will have 750,000 CPU cores. A single OpenMP program could not run on more than 128 of them. So the OpenMP is great and fantastic for getting performance up to a few dozen cores on your laptop or on a server. It's not useful for it's not on its own useful for HPC. So I think now I'll go back, if that's okay. I'm happy to answer any other questions, but I will now go to the carry on with the lecture. It should be. Oh, I did the wrong thing there. Fine. So what we're going to do, you might say, and this is actually true, okay, to parallelize this in a hybrid model. Okay, my sharing is still not very robust. Let's see if I can do that again. Fine. You might say, why don't I just take the MPI code and stick those parallel directives in? Well, actually you can, and that, that's one of the reasons I don't give out solutions here. Maybe I should, is you literally just copy the parallel directives from the OpenMP code into the MPI code. And so, so that will work. But we can identify 4 different styles of MPI plus OpenMP programming, depending on when the OpenMP threads are permitted to make MPI calls. And actually, one of the extensions to MPI to allow you to safely do hybrid MPI OpenMP programming is MPI has a threading interface. So it turns out when you initialize MPI, you can initialize it and say, okay, I am going to be doing this a level of threading. I want you to cope with that. And so what you do is it identifies 4 styles. Master only. All MPI communications takes place in the sequential part of the OpenMP program, no MPI in parallel regions. And this is the simplest style and actually relatively effective. So if I took the OpenMP directives from the OpenMP code and stuck them in the MPI code, I would have a master only. Code where there's a complete differentiation between the MPI communication, the halo swapping, and then the calculation. So when I parallelize the calculation using OpenMP, there is never any communication there. So the MPI, why it's called master only, is that, as I said, in OpenMP, if you have no OpenMP directives, it runs on the parent process on thread 0. So all communication is done by thread 0. So there's a complete separation between MPI and OpenMP, and this means the MPI library has no work to do. You don't even need a special MPI library here. It's very simple. You don't have any overhead in additional. So this is a simple way of doing it. Funneled is similar. All MPI communication takes place through the same master thread, but it can be inside parallel regions. And again, so that means you can have regions where you have multiple threads running, but within those regions, only one thread, the master thread, actually calls MPI. And again, in terms of the MPI library, it doesn't actually need to do any other work here, because it's as far as the MPI library is concerned, there's only ever one thread calling it. It's the master thread. The fact that that happens to have taken place from a parallel region is kind of irrelevant. Serialized is slightly different. Only you can allow multiple threads to call the MPI library at once, but only one thread makes MPI calls at any one time. So within a parallel region, you have multiple threads operating. Each of those threads can call the MPI library at the same time. Each of those threads can call the MPI library, but you, the programmer, make sure that they do not ever happen at the same time. And there is a directive in OpenMP called critical, which says, and that's what you would use here, if you put OMP critical around a piece of code, it says only one thread can execute this code at once. So actually, again, even in that situation, it's unlikely that the MPI library needs to have any extra functionality. Basically, because again, the MPI library is only ever being called on a node by one thread at one time. The fact is different. But the fact that there might be a different thread calling is probably, I'm not an expert on the way these work, but probably of little consequence. And I've got a student at the moment looking at this, and he's been running pure MPI codes with different MPI libraries, and he doesn't really see much overhead, whether you say I'm going to do master only, funneled, or serialized. But you do have a problem here. MPI distinguishes messages via processes. It says, I want to send a message from rank 0 to rank 7. Here, you have multiple threads within the same process. All these threads have the same rank. So if you want rank 0 thread 3 to send a message to rank 7 thread 5, all MPI can do is send a message from rank 0 to rank 7. How do you make sure that the correct thread picks up the message? Well, there's various ways of doing it, but the obvious way to do it is use tags. You tag the message with the thread ID of the cell who you want it to go to. So you do need to do some work here. You do need to be very careful about race conditions on send-receive buses. If you have multiple, if you have a thread doing communications on one buffer, you can't then have another thread doing communications on the same buffer, because you'll get garbage. So you have to be careful here. But again, it probably doesn't imply much overhead on the MPI library. It implies overhead on you, the programmer. You need to put in critical sections to make sure that you genuinely do a serialized implementation. And you also have to, yes, so TCP/IP sockets, it's a very similar considerations. But the one which you would like to do is multiple. Basically, so yes, so basically the serialized style says that you, the programmer, have to make sure that you only call the MPI library. You don't call the MPI library from 2 threads at once, and that requires mutexes or locks. But it's up to you, the programmer, to do that. And OpenMP has its built-in mutex, which is called a critical region. But yes, what you're doing is you have a mutual exclusion on access to the MPI library. And if you were doing this in P threads, you would have to have a mutual exclusion variable, which you grabbed, a lock that you grabbed called the MPI library and released the lock, which is a mutex. But in OpenMP, there is a directive called critical, which achieves that automatically. But it's up to you, the programmer, to do that. Multiple says any thread can call the MPI library at any point. It's up to the MPI library to sort things out. Probably what happens is the MPI library is full of lots of mutexes inside. That the MPI library has lots of mutual exclusion inside, which will have an overhead. So MPI can do something more than one thread. Some MPI implementations don't support this. Those which do mostly don't perform well because the MPI library was not designed for threading in mind. If we designed the MPI library today, you would design it from the outset to be thread safe. But some modern libraries, there are more modern parallel communications libraries, things like Gatsby, which are thread safe by design, or have threads built in by design, but MPI doesn't because of its history. So the master only is basically you parallelize your work loops, but you parallelize your work loops, and then you basically have so you have a separation between communications, which is done serially on the master thread, and calculation, which is so basically you just use MP to make the calculation go faster. But as I've said, the difficulty about this is you actually have to basically put OpenMP in everywhere for various reasons. Funneled is very similar. So OMP parallel creates lots of threads, okay? But if you have a send operation in the funneled, you have to do it only on the master thread. And there is a directive in OpenMP that says #pragma-omp master, only do this on the master thread, okay? Which is thread 0. However, you need so you're saying #pragma-omp master, I error equals MPI send. You need a barrier before and after the master. So you need to, this now has extra, well, in fact, there's effectively a barrier in this. The end parallel is a barrier. All the threads, you're not going to go onto this until all the threads have finished, but that's done automatically by the OMP parallel, end parallel. This spawns the threads, forks the threads, they join here, and there's effectively a barrier. If you do your if you do your MPI within a parallel region, it's up to you to make sure that only in the funneled style, that only the master thread does it with OMP master, but in practice you need a barrier before and after. Why do you need this barrier before the send? So you're doing some work which has been done by many threads, a race, but yeah, exactly, what's the race? What's the problem here? And then you're getting the master thread to send some data. What could go wrong here in a typical code? Yes, other thread, absolutely. So what you're doing is you're doing some work to create presumably some answer, which you're now sending here. But if you let the master thread send it, there's no guarantee that these other threads have completed their work. So presumably you're doing some work and sending the results of that work in the send statement. Without the barrier, the master process could send it incomplete work or modified, and you need a barrier afterwards because the other threads presumably need to receive some data, and so yes, you need a barrier afterwards to make sure that a thread doesn't alter this data while it's being sent. So in fact, as well as Matthew correctly saying other threads can modify before the send, without this barrier, other threads could modify after the send, while the send is going on. So you start to see that OpenMP, it can be a bit tricky, and combined with MPI can even be trickier. Serialized is the same, except you have a work region, then you have a critical region where the critical says only one thread can do this at once, and you might need a barrier here depending on the logic. But I mean, here you're saying we're doing work, and when I am finished my, well, what you're saying here is when I am finished my work, you probably wouldn't want a barrier here. Each thread is now calling a different send based on the outcome of its work. But you have to protect that with a critical, because you're saying you're guaranteeing in the serialized style, you're guaranteeing to the MPI library, lots of threads will be calling you, but don't worry, I'll make sure that only one thread calls you at once. And that in practice means the MPI library has doesn't need to be extended extensively. Multiple is a free-for-all, OMP parallel, work, MPI. And this, because the MPI library can be being called by multiple threads at the same time, the MPI library will need to make thread safe. It will need to have lots of locks and checks and barriers to make sure that it works correctly. So the multiple style places a lot of overheads on the MPI library. So in fact, it's probably better to do something like this or this for you to manage the interaction between threads than to offload it to the MPI library. But that's just a matter of suck it and see. So the point is, thread safety, making MPI libraries thread safe is difficult. That if there are data structures, have to lock the access to it with a mutex, as someone has mentioned, or you have multiple data structures. But there's a lot of work here, which adds significant overheads. And this may hamper standard single-threaded codes. So you'd be quite annoyed if next month Cray released an MPI library and said, we've made our MPI library thread safe. Has quite a lot of overheads, but it's thread safe. And you say, well, I don't care about threading, and your MPI code goes slower. So it's really important that you're able to tell the MPI library, look, I don't need threading, in which case it can default to the fast version, or I do need threading. So that's done at the init stage. So there's a new init call. Instead of calling MPI init, you call MPI init thread. And you say what level of thread support I need, okay? So you say, so in the new syntax, instead of MPI init of argc argv, it's MPI init, and you say what level of thread support you require, and but MPI returns to you what is provided. And so MPI does not guarantee, you may ask for multiple, but MPI may get back to you and say, I'm sorry, I don't support multiple. And you have to cope with that, either by reverting to a different style of MPI programming or quitting and saying, I'm sorry, I can't run. But MPI is not required to provide threaded support, although most libraries probably will, but it is required to tell you what level of support it can provide. And these are called MPI thread single, MPI thread funnel, MPI thread serialized, or MPI thread multiple. Okay, only one thread will execute. Funneled, we've covered these. Okay, so you would do, if you wanted to do, and these are ordered. So MPI thread single is less than thread funneled. So what you would do is you would say, please give me MPI thread multiple. Tell me what you can provide. And you can say, if provided is less than MPI thread multiple print, I can't do it. Okay. These don't strictly map onto the MPI OpenMP, because hybrid MPI is being written to deal with threaded codes, but when we say threading, we mean OpenMP. So, and here there's no distinction between master only and funneled. Okay, so thread single is sort of what we would call master only, I guess. The MPI standard has a bunch of so there's also a way of querying threads, return the current level of thread support. So you can call this at runtime and say, you know, what. So here we are, you know, if provided is less than requested, print not high enough level of thread support and an MPI abort, for example. So you can also query it. So if you were writing a library routine which required threading support in the MPI library, you would call this and then say, look, you can't do it. So that's the kind of the sort of high level, what am I trying to say? The high level view. I'm going to go through the advantages and disadvantages quite quickly. But are there any questions on that? So the model is we identify different modes of using MPI. One is only the master thread calls it. The other is only the master thread calls it, but can be from within parallel regions. The other one is that multiple threads can call the MPI library, but only one will do it at a time, and that's up to you, the user, to make sure that's what happens. And the final one is the, you know, all singing, all dancing, multiple threads can call, any thread can call the MPI library at any time. And if you use either serialized or multiple, you have different threads calling the MPI library, and you have to make sure that your program logic can cope with that, because when you send a message, it only goes to a certain process. By default, it's not identified as being belonging to a particular thread within that process. And so the way to do that is possibly to use that's a classic way of doing it. You can use communicators. That's a bit maybe overkill. Tagging is the way you do it. So I'll quickly go through the advantages and disadvantages of these. In a normal MPI program, it's possible that the intranode messages are overlap the internode ones. What I mean, it will be, sorry. So the messages which are sent off node will happen at the same time as the messages which happen on node, because they're being handled by different processes. However, if I do this, the interthread communication happens here in the loop, not here, and it won't be overlapped with you have a lot more synchronization. Whoops. You have a lot more. You have an implicit barrier here, and the interthread communication happens here. So you don't overlap. You've separated out the sort of communication between nodes and on a node, and that can have performance implications. Funneled is simple to write and maintain, and it's also possible for other threads to compute while the master is in an MPI call. Disadvantages are you're mixing the MPI and the OpenMP levels of parallelism, and this is a slight technicality, but all communicated data passes through the cache where the master thread is executing. So I mean, this won't make sense if you've not done OpenMP programming or looked at threaded programming. But the problem here is that we can get cache thrashing here. Data can end up in the wrong cache, which can end up the program will still be correct, but the performance will suffer. So, for example, if we do now, actually, one of the advantages I can see of doing funnels is this model here. So I said in some of the MPI lectures earlier on that although non-blocking communications appear to allow you to overlap communication and calculation, in practice they don't, because the MPI library is either running or it's not. It's not running concurrently with your application code. However, and I've tried this and had modest success with it, what you can do if you do hybrid MPI OpenMP is you can say, right, I've got 8 threads, okay? I'm going to use 7 of them for computation, but 1 for communication. So actually, you can overlap communication and calculation because you've done it by hand. You pick a thread, normally the master thread, to do or thread n-1, you have a separate thread to do the communications. And so what you would do here is you have some work, you do a barrier, and then if you're thread 0, you do a send, else you do some more computation, and then you finish here. So this thread, this send, will overlap with this computation and then they'll all end up at the barrier. So this does allow you genuinely to overlap communication and calculation. And in simple test programs written like this, I have been able to successfully overlap communication and calculation almost 100%. In other words, completely hide the overhead of the send behind the cost of the computation. However, although I've been able to do that in test programs where this is a dummy send and a dummy calculation, I have not been able to get similar success in real programs. The problem with this approach is you can't use the OpenMP work sharing directives here. Does anyone know why? Why can't you do OMP parallel 4 here, for example, OMP 4 in this model? So you'll only know the answer if you've done quite a lot of OpenMP programming. So the great thing about OpenMP is you don't have to say, if I'm thread 0, do iterations 1 to 5. If I'm thread 1, do iterations 6 to 10. If I'm thread 2, do iterations 11 to 15. OMP parallel 4 splits up the loop automatically for you. The problem is that the work sharing directives assume that all the threads are active, and here by definition one of the threads is doing this and the other ones are doing here, so you need to split up the work up here by hand. A bit annoying. Again, here's another one. Well, actually you can in OpenMP say, I want to do this on 2 threads, so one thread does this part, one thread does another part, and then this is called using teams, and you can parallelize within the second team. This is quite a difficult thing to get to work, and it's a lot of overhead on the OpenMP library. Serialized, this is where you have multiple threads calling the MPI library, but only at the one time. Easier for other threads to compute one as an MPI call. You can arrange for threads to communicate only their own data, but it's harder to write and maintain. And what you end up with, you have one of the things we talked about being a benefit of hybrid MPI OpenMP was aggregating messages, sending a smaller number of large messages. That doesn't happen here, and you need to distinguish between threads between messages meant for different threads going to the same process. So again, as I said here, we can use tags to do that. Multiple, it's the elegant style. If you're from a sort of more formal computer science background, this is the one you would think was the obvious thing to do. Messages from different threads can, in theory, overlap, although actually most MPI libraries will implement thread safety by serializing. Disadvantage, it's hard to write to maintain. It's not all MPI implementations support this, and most MPI implementations don't perform well. So my student who's looking at a pure MPI code, when he ran it with a threaded MPI library, he did MPI init thread, MPI thread multiple. Although he never used any of the functionality, his MPI code went slower. So there are internal overheads to this model. So summary, MPI plus OpenMP is becoming standard practice. You will see quite a lot of application codes, things like GROMACS, NAMD. I think big application codes have big users community support will support hybrid MPI OpenMP. On Archer, someone did a study, and about 30% of consumed CPU hours were on Archer. Many people saw it as the key to exascale, but thread multiple might be required, and that's very difficult to implement efficiently. Achieving correctness is hard. We have race conditions, as we saw previously. Missing out a barrier could lead to an incorrect code. Achieving performance is hard. And even once you've got a code, you've got to optimize the choice of the processes of threads and the placement. So it is quite tricky to do. Think carefully before embarking on this thing. Remember AMdahls Law, as I keep saying, just because the big mistake people make is they have a computational kernel which takes 90% of their time. They spend a lot of time optimizing it in hybrid MPI OpenMP, and it goes faster. But just because your kernel goes faster doesn't mean your whole code will, because you've still got a lot of your code which has no OpenMP in it. And the disadvantage of hybrid MPI OpenMP, you have to stress, is whenever you're not running OpenMP, whenever you don't have threads, you're running on fewer MPI processors than CPU cores. If you wrote your code right from the start to be hybrid MPI OpenMP, this can work. Loop-by-loop parallelization can be challenging, but if you introduce an OpenMP at a high level, it may be more. Well, what you can do here is you can say, I'm going to view my task as my program, my calculation is a bunch of independent tasks, and those tasks can be implemented by processes or threads, I don't care which. But that's a design decision. Many codes were written before threading was commonplace, and therefore you have to use this incremental loop-by-loop parallelization, which is challenging. And again, even given a good implementation, achieving optimal performance can require a lot of messy experimentation. So that's really that's the end of the lecture. Practical now would be to, carry on doing what you want before, potentially introduce hybrid MPI OpenMP into the traffic model. What I will do is that about 1:15, I will go through the solution to show you how it works, if that is useful to you. I don't know if there's any questions that people have, but we'll do a practical session now until 12:30. After lunch, I'll come back and talk about, a practical session until 1. After lunch, I'll have a short lecture on the RMA model, which is MPI's way of doing shared memory, i.e. having shared memory between MPI processes, and it has some disadvantages, but I think it has some big advantages as well, which is why I cover it, and we'll use the same example there. So I will now I did see that I got a question in the I got a question on the chat from Rajesh. So Nikki, Nikki, you contacted me by email. I'm happy to do a screen share session just now, or sorry, a breakout room to chat to you. So Nikki, are you online? If so, we can do a breakout session to discuss your issues. Are you online? I know you've not been able to attend the whole course. And I also saw I got a question from Rajesh. So Rajesh, is it okay if I'll answer your question just now? Is it okay if I show it to people? I mean, it's on the public chat, so I guess I will. I have to do something silly here. Apologies. Just let me. I'm sorry, I'm just getting a bit of trouble here. Sorry, something weird is going on here. Apologies. I'm having problems with my. Give me 2 seconds. I'm sorry about this. Thing's going a bit weird. Okay, so I'm going to do. I'll do a screen share. I'll do a breakout with Nikki in a second. But Rajesh had a general question. Apologies. I'm having some issues with sharing my screen. It's not happy. Oh, okay. Sorry. It's basically. Okay, I understand what's going on. It blocked. Fine. So there we go. So Rajesh had a question, which was, I have two MPI applications that are coupled by running as, so although the default MPI model is you run multiple copies of a single process, a single program, most implementations support the ability to run more than one, so to have a single MPI parallel program made up of multiple executables. So what's happening here is you're running application 1 on nprox1, that'd be 20 processes, and application 2 on 40, for example. So the question is, I've started this up with application 1 running on, and these become part of the same COM world. Okay, they're all. It just happens that some of the processes are running a different program, but they're all in the same they're all part of the same MPI program. So if I ran 20 versions of app 1 and 40 of app 2, my MPI communicator would be size 60. But Rajesh is saying, if I've started off with 20 of app 1 and 40 of app 2, is the way to redistribute the process among these applications dynamically during runtime, or request more processes than the total allocated in the beginning. So unfortunately, there isn't really. So first of all, you can't redistribute them at runtime, because once you've started up the executable, that's it. It has to run till the end. So you can't do that. I guess you're saying request more process than the total allocated to give you some free ones. But there is, even if you, the problem there is that they'll be wasted when you're not using them, or they're probably using CPU. So the right thing to do, so having two applications is really a bit of a shortcut. And I appreciate these are probably very, very complicated applications, but if imagine these were very simple programs, yeah? What you would do is just put them in a single main and have, just create a single main program and make these function calls and say, MPI init, if rank is less than 20, call app 1, else call app 2, okay? So you would manage it yourself, and then you would have complete freedom to do that. So if you were able to wrap these up into a single program, then that would solve the problem. The problem is, of course, probably these have been developed independently by different research groups and aren't compatible. So that's the problem. Yeah, one's messing up, one's the CFD solver. So unfortunately, no, I don't think there is. MPI is not really dynamic in that way. And that is one of the problems, that you don't really have the ability to do that. Because MPI is very static, so A assumes when an executable starts, it will run till the end and call MPI finalize and go away. That means you can't switch an MPI process between running program 1 and program 2. And the idea of running many of them, oversubscribing the CPUs, probably won't work, because although it's MPI processes won't be quiet. So you think you're running an MPI process which is doing nothing, but it's probably spinning around using up 100% CPU. So I'm afraid that the answer is probably no, unfortunately. You have to estimate the balance at the start. Or have a clever script which runs your program, and then if within the program you determine that there's a load imbalance, presumably, you quit and then run again with new parameters. But it's not really possible to do that, I'm afraid. Sorry about that. But it's a very good question. But MPI is quite restrictive. It doesn't have this dynamic ability. Is that okay? Sorry, I couldn't be more. So I will now do a screen share with Nikki, and we will go into a separate area.